Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 says to match each type of titration to its pH at the equivalence point for solutions at 25 degrees Celsius. Okay, so I'll just write all the different types of titrations. You could have a strong acid and a strong base titration. And its pH at the equivalence point is neutral, that's around 7. And you could also have titration of a weak acid by a strong base. And the pH at the equivalence point of this type of titration would be greater than 7. So this is because when we have a strong base, because it kind of overrides more of the pH compared to the weak acid, and bases have a pH greater than 7, then the same goes for our equivalence point. It will also be greater than 7. And then lastly, we could then have a strong acid and weak base titration. And the equivalence point for these types of titrations will be less than 7. Again, because acids have a pH that is less than 7. And since we have a strong acid compared to a weak base, at the equivalence point, the pH will be less than 7. Okay, so let's see what the junior tutor said. Titrations that are from strong bases and strong acids do not hydrolyze. pH of these salt solutions will remain 7, because the ions comprising the salts will completely ionize in water. Halides and alkali metals dissociate, do not affect or alter the concentration of hydrogen ions, as the cation does not alter H+, and the anion does not attract H+ from the water. In general, salts containing halides, except fluorine, and an alkaline metal, except beryllium, will dissolve completely. Titration from strong bases and weak acids give a pH greater than 7. The anion of the salt is derived from a weak acid and will accept the proton from the water in the reaction, leaving a hydroxide ion. And the presence of hydroxide ions makes the solution basic. On the other hand, the cation from a strong base will dissociate into an ion and will not affect the concentration of H+ ions. Lastly, contrary to the previous one, the cations from the weak base will attract hydroxide ions, leaving the H+ ions from water in the solution. The presence of H+ ions indicates that this solution is acidic. Yep, so this solution is correct. Okay, so question 2 asks, what is the difference between molecular mass and molar mass? Okay, so let me make a comparison table. Molecular mass and the molar mass. So for molecular mass, this is the mass of one molecule. And this can be of like any element. And molecular mass is also measured in atomic mass units, so also known as AMU. And typically it's only determined in molecules. If we compare this with a molar mass, this is the mass of 1 mole of a substance. It is also known as molecular weight, which is in grams per mole. And typically it is determined for different compounds and also atoms and molecules. Okay, so they're pretty similar, but they only have some minor differences. The junior tutor said that in definition, the molecular mass is defined as the mass of one molecule. It is measured as atomic mass units, or AMU. It is a relative mass of a molecule of a substance measured by the ratio of the mass of one molecule of the substance to the 1/12th part of a carbon atom. On the other hand, the molar mass is the mass of 1 mole of a substance. It is measured using grams per mole. Yep, so this solution is correct. Okay, so question 3 says that element X forms 3 different compounds with element Y. Based on the information in this table, what are the formulas of compounds 2 and 3? So they have this helpful table showing all the different compounds. And X and Y are just unknown elements, but basically they have different chemical formulas. And we're trying to figure out how many Y atoms are in compound 2 and in compound 3. They also give the mass of Y per grams of X. Okay, so let's try to break down how we would go about answering this. Let's look at compound 1 first. So everything in compound 1 is given. So we know its chemical formula is 1 X atom and 6 Y atoms. And we also know its mass of Y per grams of X. So this means that in XY6, there are 2.82 grams of Y and 1 gram of X. Okay, so since we know everything in compound 1, we can use this information to try and find out the formulas of compounds 2 and 3. So let's look at compound 2. We don't know its formula, but we do know that the mass of Y per gram of X is 1.41. So we need to find out the ratio of the Y of the mass of Y. So since compound 2 contains the same amount of X as in compound 1, so they both contain 1 gram of X, this difference in the mass is only due to the amount of element Y. So if we divide 2.82 grams from compound 1, and we divide it by 1.41 grams, and this is compound 2, then we can find the Y ratio of 1 and 2. So if we divide the two together, we get a ratio of 2 to 1 for compound 1 to 2. So therefore, compound 2 has half the amount of Y compared to compound 1. So that means its formula would be XY3. So let's do the same thing for compound 3. Compound 1 had 2.82 grams of Y, and compound 3 only has 0.94 grams of compound Y. So the ratio between of 1 to 3 is 3 to 1. So it also has less of element Y in compound 3. And if we divide Y6 by 3, you get 2. Okay, so therefore the formula for compound 2 is XY3, and the formula for compound 3 is XY2. And the junior tutor said the same explanation. To be able to answer these types of questions, you need to compare the ratio of masses given for the known chemical formula to the ratio of masses of the compounds with the unknown chemical formulas. Comparing compound 1 and compound 2, 2.82 grams of Y per 1 gram of X in compound 1, and 1.41 grams of Y per 1 gram of X in compound 2. It can be noticed that in compound 2, the mass of Y element per mass of X element is half than that of compound 1. It means that there are also half the numbers of Y elements in compound 2 than of compound 1. Therefore, the formula for the compound 2 is XY3. Comparing 1 and 3, using the same logic in this step, it can be observed that the mass of Y element or mass of X element in compound 1 is thrice than that of compound 3, and it means that the number of Y elements in compound 3 is a third of the number Y elements in compound 1, making the formula for compound 3 XY2. Okay, so this solution is correct. It was pretty well explained, even though we have to use the words compound 1, compound 2, X and Y. Like it can sound confusing, but they did a pretty good job explaining it nonetheless. Okay, so question number 4 says, what are some examples of a buffer solution? So let's define what a buffer solution is. So a buffer solution resists drastic change in pH even upon small additions of strong acid or strong base. So for example, let's say we had a solution of water. If we added the tiniest amount, like let's say like a drop of a strong acid such as HCl, like a highly concentrated HCl, then the pH of that water would decrease significantly upon that one drop of a highly concentrated acid solution. But when we have a buffer, it tends to resist this drastic change upon small additions of strong acid and base. So we can have different buffer solutions. So one example is a mixture of a weak acid plus its conjugate base, or we could have a mixture of a weak base and its conjugate acid. So an example would be hydrogen cyanide, which is a weak acid, plus its conjugate base, which is the cyanide ion. This would make a buffer solution. And the junior tutor said that a buffer is a solution that can resist drastic changes in the pH on the addition of acidic or basic components. In a buffer solution, only a small amount of the acid or base ionizes into the solution, thus maintaining a relatively stable pH. It is commonly used in processes that require stable pH ranges. Basically, a buffer solution should contain a weak conjugate acid-base pair, which means that it can be a combination of a weak acid and its conjugate base, or a weak base and its conjugate acid. Following are examples of a buffer solution. So you could have acetic acid, which is a weak organic acid with the formula CH3COOH, and a salt containing its conjugate base, the acetate ion. So this is like sodium acetate, CH3COONA. Pyridine is a weak base, and a salt containing its conjugate acid, the pyridinium cation, such as pyridinium chloride. Or lastly, you could have ammonia, which is a weak base with formula NH3, and a salt containing its conjugate acid, the ammonium cation, such as ammonium hydroxide. Yep, so this solution is correct. Okay, so question 5. What is the balanced chemical equation of the reaction of aluminum with hydrochloric acid? Question 5. Okay, so let's show aluminum reacting with hydrochloric acid. Okay, so notice that we have 3 different elements, and the most common reaction that occurs when you have just like 3 components is the single displacement reaction. So basically, the aluminum would kind of swap places with the hydrogen almost. But keep in mind that an aluminum ion has a 3+ charge. So to neutralize it, we need 3 of the chlorine ions, which have a -1 charge, in order to neutralize aluminum's 3+ charge. So I think this might be a solid. So this is one of our products, and our other product is just hydrogen gas. Okay, so now let's try to balance out this equation. So I typically like to balance atoms that aren't hydrogen, or oxygen's not here, but I usually balance like hydrogens and oxygens last. So let's just look at the other types of atoms. If we see aluminum, there's 1 aluminum on both sides. So my first step is just to balance out the chlorines. So you'll see that our product side has 3 chlorine atoms and our reactant side only has the 1. So I'm first going to put a 3 in front of HCl. So this affects the number of hydrogen atoms. So now I need to balance my hydrogens. So notice that there is an odd number of hydrogens on my reactant side, and there's an even number on my product side. So I know I need to get fractions involved somehow. So the way that I do it with like diatomic elements, such as H2, is that I usually put however many hydrogens that are in my reactant side, so 3, and then I just divide it by 2. Okay, so everything is balanced, but typically in the final balanced chemical equation, we don't really like to deal with the fractions, even though it is technically balanced. So to get rid of the fractions, we are just going to multiply the whole reaction by 2. So step 3 is to multiply. And then we should end up with 2 aluminums plus 6 HCl, which makes 2 aluminum chlorides plus 3 hydrogen gas. Okay, so let's double check to see everything's balanced. 2 aluminums, 6 chlorines, and 6 hydrogens. Okay, so the junior tutor said that a single displacement reaction is a chemical reaction in which one element is replaced by another in a compound. It can be represented generally as A plus BX produces B plus AX. The starting materials are always pure elements, such as pure zinc metal or hydrogen gas plus an aqueous compound. When a replacement reaction occurs, a new aqueous compound and a different pure element will be generated as products. This will most often occur if A is more reactive than B, thus giving a more stable product. The reaction of aluminum with hydrochloric acid is another example of a single displacement reaction. The balanced chemical equation would be 2 aluminum plus 6 HCl makes 2 aluminum chlorides plus 3 hydrogen gas. Okay, so this solution is correct. Okay, so question number 6. What types of intermolecular forces would water molecules have? Okay, so first let's draw out a water molecule. Everyone knows it as H2O. But oxygen is more electronegative than the two hydrogens. So therefore there's an uneven sharing of electrons in the covalent bonds. So because of this uneven sharing of electrons, a water molecule has a partially negative side where the oxygen is, and it has a partially positive side where our hydrogen atoms are. So if we were to have a second water molecule come in, you'll see that it also contains a partially negative side and a partially positive side. So the partially negative side of another water molecule is attracted to the partially positive side of the other water molecule. So this is called hydrogen bonding. Okay, so this specifically involving hydrogen, but it's also known as like an interaction of the dipoles. So I can also say that dipole-dipole interactions occur in water molecules as well. And another intermolecular force would be London dispersion forces. So London dispersion forces is when the electrons in two adjacent atoms occupy positions that make atoms form temporary dipoles. So these are very weak, but they're pretty common amongst almost every molecule. Okay, so 3 types of intermolecular forces would be hydrogen bonding, dipole-dipole interactions, and London dispersion forces. So the junior tutor said that to answer this question, we need to review first the concept of intermolecular forces. Intermolecular forces are forces that hold molecules together in liquid or solid. In general, intermolecular forces are much weaker than intramolecular forces, such as covalent bonds. Intermolecular forces play an important role in the melting points of solids and boiling points of liquids. The liquid boils when the molecules have gained enough energy to break the intermolecular attractive forces. In the same manner, solids melt when this molecule has enough energy to overcome the intermolecular attractive forces that hold the molecules together. There are three types of intermolecular forces. These are dipole-dipole interactions, London dispersion forces, and hydrogen bonding. The water molecule consists of two hydrogen atoms bonded to an oxygen atom. Its overall structure is bent due to the electronegativity difference in the oxygen atom. Well, it's actually bent because of the lone pairs of oxygen. That's a different story. Anyways, the oxygen atom forms hydrogen bonding with the hydrogen atom and also carries two unshared electrons that cause the difference in electronegativity. Okay. And water is polar in nature. The bonds formed by the hydrogen atoms with oxygen are called hydrogen bonds. Hydrogen bonds are weak interactions formed between hydrogen with a partial positive charge and a more electronegative atom, in this case oxygen. Hydrogen can also form hydrogen bonds with other electronegative atoms such as oxygen, nitrogen, or fluorine. Okay, so I'm just going to say this part is correct. So it gets kind of confusing when you try to think about hydrogen bonding, because people tend to think that it is the bond that is formed with hydrogen and oxygen and like a water molecule. But the actual concept of hydrogen bonding is because of that partially positive side of a molecule reacting with the partially negative side of another molecule. So this is the actual hydrogen bonding. So in the case of the junior tutor, when they said that the oxygen atom forms hydrogen bonding, well, I think this part, bonds formed by the hydrogen atoms with oxygen are called hydrogen bonds. I think they might have just misunderstood the scenario. But yep, so hydrogen bonds are the weak interactions formed between hydrogen with a partial positive charge and a more electronegative atom, in this case oxygen. Okay, so hydrogen bonds are weak interactions formed between hydrogen with a partial positive charge on one molecule and a more electronegative atom, such as oxygen, on a different molecule. And then I'll say that dipole-dipole interactions and London dispersion forces take place as well. Okay, so question number 7. What is the oxidation state of an individual sulfur atom in barium sulfate? Okay, so let's define what an oxidation number is. This is the charge that an atom would have if the compound was composed of ions. Okay, so let's look at barium sulfate. We can separate it into its ions to make it easier for us to find the oxidation numbers. So SO4 is an example of a polyatomic ion called sulfate, and it has a charge of 2-. So if we were to break apart barium sulfate, barium has a 2+ charge, and the sulfate ion in total has a 2- charge. So there are different rules when you need to find the oxidation number, and one of the main ones is that oxygen tends to have an oxidation number of -2, except when it is in a peroxide, it would have a -1 oxidation number, but in this case, it has an oxidation number of -2. So notice that there are 4 oxygen atoms. So each oxygen atom, well, each of it contributes the -2 charge, and we have 4 of it, so it has a total of -8. So the oxidation number of sulfur needs to be +6. And we know this because since the sulfate ion has an overall 2- charge, we know that the sulfur isn't going to have an oxidation number of +8 because it's not neutral. So in order for the sulfate ion to have a -2 charge, the oxidation number on sulfur can be +6. And then barium just has its 2+ charge as its oxidation number. Okay, so let's see what the junior tutor said. By definition, the oxidation number of an atom is the charge that an atom would have if the compound was composed of ions. It is altered as an oxidation state as it indicates the total number of electrons that an atom either gains or loses in order to form a chemical bond with another atom. To determine the oxidation number of the nitrate, and I think they mean the sulfate ion, we have to consider some rules. The important rules are the oxidation number of oxygen in a compound is usually -2, except in peroxides where it is -1. Nitrogen compounds, on the other hand, encompass oxidation states of nitrogen ranging from -3, as in ammonia and amides, to +5, as in nitric acid. The sum of all the oxidation numbers in a polyatomic ion is equal to the charge of the ion. So therefore, we let X equal the number of sulfur in barium sulfate, and the oxidation number of barium is +2, and for oxygen it is -2. Okay, so they showed how if you had the sum of all of those oxidation numbers in barium sulfate, it should equal to 0. So then they just solved for X and got +6. Yep, so this solution is correct. Okay, so question 8. What are the intermolecular forces between the molecules of methanol? Okay, so let's draw out a methanol molecule. Okay, so this is the structure of methanol, and you'll see that it has a carbon bonded with 3 hydrogens and also an oxygen. And if we note the electronegativity values of carbon and oxygen, you'll see that carbon is much less electronegative than the oxygen. So this means that there is an uneven share of electrons in the carbon and oxygen bond. So we can draw a dipole moment going towards the direction of the oxygen since it is more electronegative. It tends to pull the electrons more strongly than our carbon atom. So because of this uneven sharing of electrons, the methanol molecule contains a partially negative side in the direction of the alcohol group and a partially positive side. So what happens when we have multiple molecules of methanol is that the partially negative side of one methanol molecule would be attracted to the partially positive side of another methanol molecule. So this attraction is called hydrogen bonding. So that's one example of an intermolecular force. And this is how multiple methanol molecules can be attracted together. I'll just draw another one for good measure, just kind of showing that that is what hydrogen bonding is. So similarly, this is also known as like a dipole-dipole interaction. Hydrogen bonding is just specifically involves hydrogen. And lastly, another intermolecular force that can take place is called London dispersion forces. So when we have London dispersion forces, this is when the electrons in 2 adjacent atoms occupy positions that make atoms form temporary dipoles. Okay, so these are 3 different types of intermolecular forces that can take place between the molecules of methanol. So the junior tutor said, to answer this question, we need to review first the concept of intermolecular forces. Intermolecular forces are forces that hold molecules together in a liquid or a solid. In general, intermolecular forces are much weaker than intramolecular forces such as covalent bonds. Intermolecular forces play an important role in the melting points of solids and the boiling points of liquids. The liquid boils when the molecules have gained enough energy to break the intermolecular attractive forces. In the same manner, solids melt when the molecule has enough energy to overcome the intermolecular attractive forces that hold the molecules together. There are three types of intermolecular forces. These are dipole-dipole, London dispersion, and hydrogen bonding. Image below shows the molecular structure of methanol. So methanol molecules contain oxygen and hydrogen, which has a high difference in terms of electronegativity. This results to dipole-dipole interactions between the partially positive hydrogen and partially negative oxygens of two separate molecules. This is called hydrogen bonding, which is an extreme type of dipole-dipole interaction. So let me just make sure that this is correct. When dipole-dipole interactions between the partially positive hydrogen on one molecule partially negative oxygen on another is called hydrogen bonding. Okay, so question number 9. This asks, what is the difference between polar and nonpolar covalent bonds? Okay, so when we have nonpolar covalent bonds, this is when two atoms have an equal or similar electronegativity values. So we can also show that the difference in electronegativity is around 0 to 0.5. Okay, so let's have an example. So some examples would include like diatomic molecules, so such as the nitrogen-nitrogen bond is considered nonpolar covalent since obviously it is the same atom. Its difference in electronegativity would just be equal to 0. Let's also look at the carbon-hydrogen bond and calculate its difference in electronegativity. I'm just going to Google electronegativity values. And you'll see that carbon has an electronegativity value of 2.5. And hydrogen has an electronegativity value of 2.1. So the difference between the two is only 0.4. So this lies in the range of 0 to 0.5. So that makes our carbon-hydrogen bond a nonpolar covalent bond. Okay, so now let's define what a polar covalent bond is. So when we have a polar covalent bond, this is when two atoms have dissimilar electronegativity values, and it leads to a dipole moment. Okay, so typically the difference in electronegativity for polar covalent bonds can range from 0.5 to around 1.69. Okay, so let me underline this as well. And let's look at some examples. So let's say we had the bond between oxygen and hydrogen. So let's calculate its difference in electronegativity. Oxygen has an electronegativity value shown here at 3.5, and hydrogen's is 2.1. So this difference in electronegativity is 1.4. So this lies within the range 0.5 to 1.69. So this makes the oxygen-hydrogen bond a polar covalent bond. So another example of a polar covalent bond would be between like phosphorus and fluorine. So another thing to note with polar and nonpolar covalent bonds is that these only occur between two nonmetals. So when we have these differences in electronegativities, these are going to be between the two nonmetals, because there is also something called an ionic bond. Let's do this in orange. Ionic bonds are between a metal and a nonmetal. And typically, they tend to have an electronegativity difference that is much higher, so greater than 1.7. An example would be like potassium fluoride. So the minute you see a metal that is involved in the bond, it's automatically not a covalent bond. It would be considered an ionic bond. So even if you, like let's say we calculated the difference in electronegativity of two nonmetals, and it was greater than 1.69, the fact that it contains two nonmetals already means that it is not an ionic bond because it was between two nonmetals. So that's why you need to be careful when you calculate the difference in electronegativity of two atoms, because even if it doesn't lie within this range, it all depends on whether or not it takes place between two nonmetals or if it was between a metal and a nonmetal. Okay, so that's just like a little disclaimer. So that's why these ranges are kind of averaging out, because sometimes you might have two nonmetals, but their difference in electronegativity is like 1.71. So it wouldn't be considered ionic because it was two nonmetals. So the junior tutor said that covalent bonding happens when electrons are shared between atoms or molecules to attain stability or an octet. A covalent bond that has an equal sharing of electrons is called a nonpolar covalent bond. On the other hand, a polar covalent bond are formed when a pair of electrons is unequally shared between two atoms. Yep, so this solution is correct. Then I just also added that due to differences in electronegativity between two atoms. So let me just say that this typically greater than 0.5. This leads to an uneven share of electrons between atoms, so polar covalent bonds. Then I'll also add that the carbon-hydrogen bond is considered a nonpolar covalent bond because and then I just also added that the carbon-hydrogen bond is considered a nonpolar covalent bond because the difference in electronegativity between carbon and hydrogen is only 0.4. But this solution is correct. So those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can leave it a thumbs up and a comment. And don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.